Alright, so welcome. I'm going to do an after work video today. It's been a while since I've done these, but I'm feeling a lot of good energy. So I go and do something at 6, so I'll have plenty of time to do a substantial video. I'm thinking this energy might have come from the last video where I got stung in the foot twice by something that I still have not identified. It seemed to have given me superhuman strength and focus to study for this exam, which is a good thing. I desperately needed that. Okay, so here's the upload of the last video. So this video will just be continuing on with where I left off, which was just reading the documentation that specifically calls out the traffic engineering database. And I did make a note of where I would start reading next. So we're going to start with assigning credibility values. Okay, and then I'll need to highlight this as well, because we're going to be skipping down and only focusing on where this search term is mentioned. Okay, so this is assigning credibility values. Once the entries are installed in the traffic engineering database, the BGP-TE learned information is made available for CSPF computation. The traffic engineering database, and I'm curious because I watched my last video a little bit, and the audio seemed a little bit strange, so I'm just wondering if there's a way I can fix that somehow. Okay, I just wanted to verify that it was taking audio from the webcam, and it is. So once the entries are installed in the traffic engineering database, the BGP-TE learned information is made available for CSPF path computation. The traffic engineering database uses a protocol preference scheme that is based on credibility values. A protocol with a higher credibility value is preferred over a protocol with a lower credibility value. BGP-TE has the capability to advertise information learned from multiple protocols at the same time. And so, in addition to the IGP-installed entries in the traffic engineering database, there can be BGP-TE installed entries that correspond to more than one protocol. The BGP engineering database export component creates a traffic engineering database protocol and credibility level for each protocol that BGP-TE supports. These credibility values are configurable in the CLI. The credibility order for the BGP-TE protocols is as follows. And remember, the highest is the most credible. So just like regular routes, we've got directs are going to be the most credible, static second most credible, and then it depends on the protocol being used. So it looks like ISIS is considered more credible than OSPF. Okay, so let's skip down to the next section, which is going to be flow of BGP link state spring data. I'm not sure what that is, but they do mention the traffic engineering database quite a bit, so let's give that a read, and we'll just read down to here. So figure 2 depicts the data flow of BGP link state spring data that ISIS pushes into the traffic engineering database. IGP, in this case ISIS, pushes the spring attributes to the traffic engineering database. Spring capabilities and algorithm information are carried forward as node attributes into the traffic engineering database. Adjacent SID and LAN adjacent SID information are carried as link attributes. Prefix SID or node SID information is carried as prefix attributes. A new set or a change to existing attributes triggers IGP updates to the traffic engineering database with new data. RSVP is a prerequisite for link attributes. Caution, if traffic engineering is disabled at the IGP level, none of the attributes are pushed to the traffic engineering database. All parameters in the BGP traffic engineering NORI, network layer reachability information, including the link, node, and prefix descriptors, are derived from entries in the traffic engineering database. The traffic engineering database imports route entries into the latest LSDIST.0 routing table from IGP subject to policy. The default policy of BGP is to export routes, which are known to BGP only. You configure an export policy for non-BGP routes in the LSDIS.0 routing table. This policy advertises an entry learned from the traffic engineering database. Okay, and this next mention, Junos OS does not support the following features for BGP link state with Spring extensions. Traffic engineering database export for Spring parameters. So I'm kind of not getting the best sense here from this strategy, but I don't have enough time to just read through this whole thing. I really do need to make my time targets. But here we have verifying traffic engineering database entries, which is something I probably will need to do on the exam. So, okay, so there's two different So this we already read before. I think I'm just going to read it again because it seems like a good thing to. This is probably what is on the exam, these path error messages. So this is improving traffic engineering database accuracy with RSVP path error messages. An essential element of RSVP-based traffic engineering is the traffic engineering database. The traffic engineering database contains a complete list of all network nodes and links participating in traffic engineering, and a set of attributes each of those links can hold. For more information about the traffic engineering database, see constraint path LSP computation. So this is a good one because this is specifically more information about. Yeah, and I believe I already read this whole thing before. Yes, I did. I remember reading this whole thing before. I'll include it in the notes just so that it's. And I'll say also related. Okay. One of the most important link attributes is bandwidth. Bandwidth availability on links changes quickly as RSVP LSPs are established and terminated. It is likely that the traffic engineering database will develop inconsistencies relative to the real network. These inconsistencies cannot be fixed by increasing the rate of IGP updates. Link availability can share the same inconsistency problem. A link that becomes unavailable can break, and I just remembered my icon is a bit small, so I will make that bigger. This is why I have trouble keeping focus. As I was reading that thought was in my head, and you can see it's costing me a lot of time. So let's keep focused and let's keep reading. Bandwidth availability on links changes quickly as RSVP LSPs are established and terminated. It is likely that the traffic engineering database will develop inconsistencies relative to the real network. These inconsistencies cannot be fixed by increasing the rate of IGP updates. Link availability can share the same inconsistency problem. A link that becomes unavailable can break all existing RSVP LSPs. However, its unavailability might not be readily known by the network. When you configure the RSVP error hold time statement, a source node ingress of an RSVP LSP learns from the failures of its LSP by monitoring path error messages transmitted from downstream nodes. Information from the path error messages is incorporated into subsequent LSP computations, which can improve the accuracy and speed of LSP setup. Some path error messages are also used to update traffic engineering database bandwidth information, reducing inconsistencies between the traffic engineering database and the network. You can control the frequency of IGP updates by using the update threshold statement. See the configuring RSVP update threshold on an interface. So I believe we did a lot of that last video. But let's let's just read this whole thing. Path error messages. Path error messages report a wide variety of problems by means of different code and subcode numbers. You can find a complete list of these path error messages in RFC 2205, Resource Reservation Protocol, RSVP, version 1, functional specification, and RFC 3209, RSVP-TE, extensions to RSVP for LSP tunnels. When you configure the RSVP error hold time statement, two categories of path error messages, which specifically represent link failures, are examined. Link bandwidth is low for this LSP. Requested bandwidth unavailable, code 1, subcode 2. This type of path error message represents a global problem that affects all LSPs transiting the link. They indicate that the actual link bandwidth is lower than that required by the LSP, and that it is likely that the bandwidth information in the traffic engineering database is an overestimate. When this type of error is received, the available link bandwidth is reduced in the local traffic engineering database, affecting all future LSP computations. Link unavailable for this LSP. Admission control failure. I think I'm going to skip that. So identifying the problem link. Each path error message includes the sender's IP address. This information is propagated unchanged through the ingress router. A lookup in the traffic engineering database can identify the node that originated the path error message. Each path error message carries enough information to identify the RSVP session that triggered the message. If this is a transit router, it simply forwards the message. If this router is the ingress router for this RSVP session, it has the complete list of all nodes and links the session should traverse. Coupled with the originating node information, the link can be uniquely identified. Configuring the router to improve traffic engineering database accuracy. To improve the accuracy of the traffic engineering database, configure the RSVP error hold time statement. When this statement is configured, a source node ingress of an RSVP LSP learns from the failures of its LSP by monitoring path error messages transmitted from downstream nodes. Information from the path error messages is incorporated into subsequent LSP computations, which can improve the accuracy and speed of LSP setup. Some path error messages are used to update traffic engineering database bandwidth information, reducing inconsistencies between the traffic engineering database and the network. To configure how long MPLS should remember RSVP path error messages and consider them in CSPF computation, include the RSVP error hold time statement. Okay, so let's move on to the Relev. You know what? I think this is gonna do it for this. I just want to make sure that I go through these verification. Yeah, so verifying traffic engineering database entries. So I just want to do that. So let's go to the lab and see how things are different. Okay, so we'll open up PE1 because it has an LSP to PE2 already. Okay, so here's the verification. Oops, so they have BGP set up on theirs. I don't have it on mine. Let's take a look at the configuration a little bit, get a better sense for what this lab is actually doing. So this is configuring a link state distribution using BGP. This example shows how to configure BGP to carry link state information across multiple domains, which is used for computing paths for MPLS LSP spanning multiple domains, such as inter-area TE LSP, and providing a scalable and policy-controlled means for external path computing entities such as ALTO and PCE to acquire network topology. So yeah, I'm not sure this is going to be on the test, but I am interested. Yeah, so you can see they have, so I think they're going to have no CSPF enabled on here. Okay, so they don't have no CSPF, but they do have a special CSPF command here, cross credibility CSPF. And that's under protocols MPLS. Oh man, if they want me to create a import policy and an export policy for the traffic engineering database, oh man, it's like, how badly do they want me to fail and never take it again? Oh man, that would just be a nightmare if they wanted me to do that. Let's see if that special command for CSPF is on there. So I'm going to do edit protocols MPLS. I'm going to do help, and then apropos star pipe match CSPF. Okay, and now you can see we've got all these set commands. But let's do another pipe match, and then we'll do begins with SET. There we go. Then we don't have those descriptions in here. So now we've got the classic no CSPF that's on there that I thought would have been necessary, but instead we've got this. So let's take a look at the question mark for this. So it's compute paths across multi-protocol links and no DES. I guess I'm not sure. Let me see if I can get a cleaner. Oh, okay, and nodes. Okay, yeah, because there's a new line break there. So compute paths across multi-protocol links and nodes. So this, so you've got two options when it comes to inter-area LSPs. You can either disable CSPF or you can enable cross-compatibility or cross-credibility, and you can share the calculations. And it looks like there's extra. Oh, right, because you can just toggle knobs in one command. It's a knob. So, all right. So let's let's just leave that off for now, because okay. I guess I'm tempted to just try to do this. Let's do a show MPLS LSP. Okay, so we do have two LSPs here from the prior lab. So I guess I'm tempted to just tear these two down and then just go with their LSPs. Let's actually do that. I've got a good like 20 minutes, so that's plenty of time. So I'm not going to follow exactly what they have here, but I will look at their two endpoints of their LSP. So they've got an LSP here on their R0, and then they've got an LSP on R3 as well, I think. Nope, so it looks like they've just got one unidirectional LSP. It's not about functionality, it's just about learning. Yeah, you know what? I think it's the topology is just a bit too different because they've got, you can see my topology here. Right now, I would have to separate them into different autonomous systems with different IGPs, which might be a good exercise for me. So I'm kind of torn because it's like, do I want to kind of get into the weeds? Especially since I only got like 20 minutes. And the answer to that is yes, but it's not really a question of do I want to, it's a question of can I. So the next topic would be, yeah, so you know what, let's get into the weeds. And I might even just go ahead and put another video into this. But yep, so let's get a topology that is kind of more similar to what they've got here. I mean, it's not going to be exactly what they have here, but hopefully I will understand it enough to be able to configure it a little bit differently. Okay, so mine is going to have some extra routers in it. Okay, so I'm gonna have these endpoint. I'm gonna have endpoint routers at the edge of the autonomous systems. So let's make the PE ones at the end, and then let's make the P1 and P2 here. All right, and then I'm gonna have additional routers. So on this side, let's just have one additional router like this. And then on this side, let's have two additional routers like this. All right, and then let's cable it up 0 to 0, 1 to 1. Okay, and then 1 to 1. And 0 to 0. Okay, and now we'll have 2 to 2. Okay, and then 1 to 1. All right, and then 0 to 0. Okay, and then we're going to have two autonomous systems just like they have there. So I'm going to draw like a square or something. Yeah, draw a rectangle. There we go. Oops, and I'm going to make sure it's not tied to that, and I'm going to send it to the back. Okay. And hopefully make it bigger if I can. Okay, so that looks good. And this is going to belong to 65534, and it's going to be in ISIS. It's not letting me, okay, there we go. All right, and then we're going to have one more rectangle here sent to the back. Excellent. All right, so now this is going to be OSPF. It's going to be 65533. Oops, and I'm selecting both, so I just want to select one. There we go. So this looks good. So now we're going to be configuring it, and it's going to be a little bit different. I think I'm going to start by just blanking out the configs, because it's going to be really good practice for just knowing how to do this. I might go with different IP addressing conventions as well, but I'm definitely going to blank them out. That might be the end of this video. But you know, that will give me a great head start for the lunchtime video tomorrow, or if I've got enough energy, the evening video. All right, so now I've got to add some back in. There we go. Oh, and I can rename it however I would like now. I'm just going to keep the same names. It's easier to blank out the config that way. And I don't think it really matters that much, at least not for this lab. For some labs where there's more clear device worlds, it'll matter a lot. Oops, so it looks like I've got PE2 in here twice, but hopefully it's, yep, okay, it's already blanked out. So we've just got one more left. That's really good news. Okay, so everything is blanked out. I've still got a good 5-10 minutes. I guess I'm just going to, let's see here, so, oops. I think I'll, I guess I'm tempted to configure some IP addresses on here. So that's interesting. I was wondering why this looks so strange to me. It's because they used a dot instead of a slash here. It's kind of interesting that it stuck out to me so much. It makes sense that it would, because let's see here. So yeah, let's do some IP addressing. Okay, so we'll start on PE1, and then we'll finish all of the, well, you know what, well, let's just do the, well, I guess I'm tempted to do the descriptions, but I might as well just do the addressing since the labeling seems to be pretty clear. And let's just do 0.1 so it looks more clear in our output. Okay, slash, and then this will be 1/30. Okay, and then this will be .1 will be 2/30. Okay, and now P3. Okay, and then this is going to be 3.1. All right, so on to P4. Okay, so these three routers are good, so I'm going to commit on all three of them, and then probably even close, well, I'll close PE1. I'll keep those other two open from now, but I'll close the console to PE1, and then I'll remember to commit PE3, and then I'll configure P1, and then I'll be able to close those two connections. Yeah, so already I'm kind of forgetting. So let's go on P3, and okay, so it's going to be 3.2 for this one. Okay, and then 0. It's going to be 4.2. Okay, and then 2 is going to be 5.1. Oops, now is that 2? Yeah, it is 2, okay. Okay, so this is going to be 5.2, so I can close this one, and this one, and now I can configure this one with 5.2. Okay, and then the other port, which is going to be port 1 with 6.1. Alright, so now it's time for P5, and that's going to be 6.2. Okay, and then 7 will be the final subnet, and it'll go on interface 0. It's going to be .1. Okay, so now I can close all of them except for the last one, which is going to have 7.2. Assuming I committed, I did. Okay, so that's good to go. Yeah, I've only got 8 minutes, well, more like 3 minutes because I leave 5 minutes early. So that's going to be the end of this video. Stay tuned for the next one when I kind of come up with my own version of this lab. Alright, stay tuned. Thanks for watching.